In this video we're going to be looking at how we can find the magnitude of a 3D vector. Before we do that, let's recap how we find the magnitude of a 2D vector. So we saw in an earlier video that if we had a vector v that's a 2D vector given by an x and a y component, that we can find the magnitude of v, which can be noted with a double vertical line before v and a double vertical line after v. So we can find the magnitude of v as equal to the square root of x squared plus y squared. And we saw that this came from thinking about our vector as being a directed line segment. And if we take that line segment and then we could construct a right-angled triangle such that that line segment is the hypotenuse of the triangle, we saw that we could apply Pythagoras' theorem to this triangle in order to find the length of that line segment. We then went on to discuss how this was very similar to a problem that we encountered in volume 1 of this training series, where we found the distance between 2 points in 2D space. So if you recall from volume 1, if we had 2 points in 2D space and we had the point x1, y1 and the point x2, y2, we could find the distance between these points as equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. So what we're saying really is how far have we travelled in x squared plus how far have we travelled in y squared, which is the exact same thing we were doing with our vector. We know that our x component tells us how far have we travelled in x, and we're squaring it, and our y component tells us how far have we travelled in y, and we're squaring it. But we also, in volume 1, we saw this was the distance between 2 points in 2D space. We actually extended this to prove how we can find the distance between 2 points in 3D space. So if we had 2 points, and these points were given by x1, y1, z1, so it is in 3D space, and x2, y2, and z2. We actually spent quite a lot of time proving this thoroughly, how we can find the distance between those 2 points. And we saw that this distance is equal to x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. So we found that the distance is equal to how far have we travelled in x squared plus how far have we travelled in y squared plus how far have we travelled in z squared. Now let's think about our 3D vector for a second. If we had a 3D vector v, which was equal to x, y, and z, what do the components of this vector tell us? They tell us how far have we travelled in x, how far have we travelled in y, and how far have we travelled in z. So can we not think of x as being how far have we travelled in x, y as being how far have we travelled in y, and z as being how far have we travelled in z, much in the same way as we did with our 2D example where we saw x2 minus x1 became x and y2 minus y1 became y? Well, yes, we can. So we can find the magnitude of a 3D vector very simply as being, so the magnitude of v as being the square root of what we have, x2 minus x1 squared, so that's how far have we travelled in x squared, plus how far have we travelled in y squared, plus how far have we travelled in z squared. So the magnitude of our vector, our 3D vector, is the square root of how far have we travelled in x squared plus how far have we travelled in y squared plus how far have we travelled in z squared. It is the sum of the squares of each of our components. We then take the square root of that. So we square our first component, we add that to the square of our second component, we add that to the square of our third component, and then we find the square root of that result. And just like in the 2D case, we're dealing with a length here. We're interested in the length of that vector, and that means we only take the positive square root. We don't worry about the negative square root because we're only worried about the positive square root. So there's really nothing to the magnitude of a 3D vector. It's just a simple extension again of the 2D case. In this case, we've used the 3D Pythagorean theorem, if you will, the extension of Pythagoras into 3 dimensions, just as we did in volume 1, where we found the distance of 2 points in 3D space, and we've used that to find the length of our 3D vector. So the only important thing really that you need to remember from this video is that if our vector v is equal to x, y, z, so it's a 3D Cartesian vector with an x component, a y component, and a z component, the magnitude of that vector is equal to the square root of x squared plus y squared plus z squared. So that's the only thing that you need to remember. And we can see that it's just a very simple extension of the 2D case, because if v was equal to xy, then we saw that the magnitude of v is equal to the square root of x squared plus y squared. So it's only a very simple extension of the 2D case involving our z coordinate. So now that we've seen this, I'm just going to ask just a couple of questions. There's not really that much to test, but I just want to test a couple of questions to make sure you are comfortable with finding the magnitude of a 3D vector. So I'm going to scroll down, and the first question I'm going to set is if we have a vector A and it is equal to, let's say, 2, 1, and 4, then I'd like you please to find the magnitude of A. And if this isn't a nice round number, then you can leave it in square root form. So what is the magnitude of the vector 2, 1, 4, please? So go ahead and answer this. When we come back, I will work through the answer here on the whiteboard. Okay, welcome back everyone. So we know the magnitude of our vector A is going to be equal to the square root of x squared plus y squared plus z squared. That means it's equal to the square root of 2 squared plus our y component squared, so 1 squared, plus our z component squared, so 4 squared, which is equal to the square root of 2 squared is 4, 1 squared is 1, 4 squared is 16. So 4 plus 1 plus 16, which is equal to the square root of 21. So again, I said, because it's not a nice round number, we can just leave that in square root form. If you did go ahead and use a calculator to work this out, you'd have found that the square root of 21 is approximately equal to 4.58. So if you got a value around 4.58, then that is the correct answer. So there's really nothing to it. All that was required is remembering that we find the magnitude of a 3D vector as the square root of x squared plus y squared plus z squared. As long as you remembered that and plugged in the 3 components correctly, squared them correctly, and then worked out the result, you should have got the correct answer. So I'm going to set one last question. I am going to use a new clean whiteboard for that. This is just going to be another question, more of the same. So question 2, if we had a vector b, and that vector was equal to, let's say, 6, minus 4, and minus 2, let's say, then what is the magnitude of this vector b? So what is the magnitude of vector b? Go ahead and give this an attempt. Once you have an answer, or if you get stuck, unpause the video and I will work through the solution here on the whiteboard. Okay, welcome back everyone. So we're finding the magnitude of a 3D vector. We know in order to do that, we're going to use our equation that says the magnitude of a 3D vector is equal to the square root of x squared plus y squared plus z squared. That means it's equal to the square root of 6 squared plus minus 4 squared plus minus 2 squared, which is equal to the square root of 6 squared. I actually should work out what the square root, or the square of 6 is rather, my apologies. So 6 squared is 36, plus minus 4 squared is going to be positive 16, so plus 16, plus minus 2 squared is going to be 4, so plus 4, which is equal to the square root of, well, 16 plus 4 is going to give us 20, and 20 plus 36 is going to give us 56. So it's equal to the square root of 56. So I'm going to leave that in its square root form, but we could, if you were to use a calculator to work this out, you get a value approximately equal to the length being 7.48 units. So once again, nothing really to it. Only key is to remember that the magnitude of a 3D vector is equal to the square root of x squared plus y squared plus z squared. And again, just like our 2D example, just to reiterate this, the magnitude of a 3D vector is nothing more than the length of the 3D line segment, if you will, as represented by that vector. So magnitude just means the length. We're finding the length of that 3D vector. So that is going to conclude this video. Thanks a lot for watching, everyone.